So hi guys, so in this lecture we'll be discussing on a problem to find the forces in x and y. So based upon law of conservation of momentum, so which we have already discussed in the previous chapter. So the sample problem, here we have a 45-degree reducing bend. So we have a bent pipe, so it is a reducer again, which means that there is a difference in diameter from inlet and exit. So reducer bend is connected in a pipeline. So we have a pipeline, so in this pipeline we have this reducer bend which has been connected. The diameter at inlet and outlet of a bend is 600 mm and 300 mm respectively. So at inlet is 600 mm, at outlet is 300 mm, so the diameter has been reduced. Find the force exerted by water on the bend if intensity of pressure at inlet to the bend is 8.829 Newton per centimeter square. So inlet pressure is given, this is 8.829 Newton per centimeter square, and rate of flow of water is 600 liters per second. So the discharge of fluid is also given. So here we need to find force exerted by the water on the bend. So it is a force that is being exerted by the water on this bend. So if the bend is able to withstand the force, then it's okay. If it's not, then there might be some catastrophic failure, there might be some breaches in the pipe. Right. So given the theta value is angle of a bend, 45-degree diameter at inlet. So convert in terms of meters, so 0.6 meter. So area will be pi by 4d square, so 0.2827 meter square. Diameter outlet is 300 mm, so area at outlet will be 0.07068 meter square. Pressure at inlet is 8.829 Newton per centimeter square, so we can convert into meter square, so into 10 power 4. So 8.829 into 10 power 4 Newton per meter square. That's why I've already been saying that convert every terms into a standard value. So in terms of meters and in terms of forces in terms of Newton. Okay. So times in terms of seconds. Even it's given in terms of hours or minutes, we have to convert in terms of seconds. Right. Okay. So pressure at inlet is given. So discharge is also given in terms of liters per second. Already we know that 1 meter cube equal to 1000 liters. So if we need to convert into meter cube, so 600 by 1000 will be equal to 0.6 meter cube per second. So the velocity at inlet will be equal to discharge by area, because we know that the discharge formula VQ equal to velocity into area. So velocity will be equal to Q by A. So Q is known, discharge. Area of section 1 is being known, so we can be able to find the velocity 1. Same way you can find the velocity at 2. So if the both velocities are known, by applying the Bernoulli's equation at section 1 and 2, so P1 by rho g plus V1 square by 2g plus Z1, which is equal to P2 by rho g plus V2 square by 2g plus Z2 for an ideal fluid. So plus head loss will be there for a real fluid. So we are not considering the head losses until it has been specified in a problem. If nothing has been specified, we're going to consider there is no head loss. It just means there is no loss in energy. So it's a horizontal pipe. So it is given that a reducing bend. Okay, so if it is given in terms of vertical, so then there will be some difference in datum. From section 1 to section 2 there will be difference in some datum. So there is no datum difference is given. So we can assume that pipe is horizontal. So Z1 will be equal to Z2. There is no difference in height level. So this becomes P1 by rho g plus V1 square by 2g equal to P2 by rho g plus V2 square by 2g. So putting the values of all, the unknown is P2 by rho g. So we're going to find the P2 value. So by simplifying this, we can able to find P2, which is equal to 5.45 into 10 power 4 Newton per meter square. So now we have known P1, P2. So because we need to find P1, P2, because for finding the force exerted by the water on the bend. So we need to know the pressure values. What is the pressure force? Okay, so the f of x, this is a formula to find the force exerted by water on the pipe bend in x direction. So this derivation we have already discussed, and we have found the formula. So by substituting these values in this formula, we can able to find the forces in x direction, which is equal to 19,911.4 Newton. So again we have to find f of y, so force exerted by a water on a bend in y direction. So this formula again we have derived. So substituting the values in this formula, so you can able to find the values in y direction, so which is 6,322.2 Newton. So here the negative sign indicates the y is acting in the downward direction, which is opposing, right? So the resultant force from a basic trigonometrical formula, so we know that resultant force will be equal to f of r square will be equal to f of x square plus f of y square. So f of r will be equal to square root of f of x square plus f of y square. So the resultant force will be equal to these values. So the angle made by the resultant force, what is an angle that is being made by this resultant force? So the angle which is already given is the angle made by the bend, but we know to find what is the angle made by the resultant force. This force, we're going to find what is an angle. So to find that angle, tan theta equal to opposite by adjacent. So opposite is f of y, adjacent is f of x. So f of y by f of x. So we're going to put the value. So theta equal to tan inverse of this value, we're going to get 17.63, 17 degrees, 36 inches. Right. So that's it. So here the total forces that is being exerted by the water on the bend is this value, total value. Okay, right. Thank you very much, guys. Hope you have got few basic ideas on the momentum equation. Thank you.